the new concept that we have is called viscosity. So what is viscosity means here for liquids? Imagine we have two types of the liquid here. So one is like a glass of the water, and the other one, we have a jar of honey. So you can see honey, everybody knows that honey is the sticker and then the water. So if you're just going to try to just pour the water, it can be easily poured, but honey is not because it's very sticky. So in this case, this kind of like a sticky, or in expression we can call it like this is more viscose, okay, or viscosity of the honey, which is like the thicker, is like the much higher than the water. So, and that is the resistance for running the flow, or running the like the flow of that kind of like a liquid. So this kind of like a viscosity is some sort of like an internal friction between in fluids, for example, and resistance to flow of or movement. Or more formally, we can just say that is like the shear stress in the liquid is more, or resistance or to shear stress is more. So this is like some sort of like a concept, if you can imagine. And we have like a lookup table. For example, this is taken from our reference book. For each type of the fluid, for example, even air, fresh water, mercury, and different paraffin oil, or like the oil at the different like the levels of the like the 10 or with the level of the 30, you can see here the viscosity change and viscosity. And here, just bear with us, this is like the coefficient of the viscosity, but we'll get back to this point exactly later in a few slides later. And you can see here the viscosity, we have some specific viscosity, and also this like the table is taken for the viscosity at like a 20 degree centigrade. So for example, and the density of the water at 20 degrees is like the 998.2, okay, and the air is like 1.2 kilograms per cubic meter. And the same for like mercury is like a 13,554. Paraffin oil is like 800. Oil at the two different levels of the 10 and 30 degrees. SAE is like the one standard for that. Is like the 880, between 880 and 950, or 880 is like 950, the same actually, but viscosity are different. So this like the oil that you might just have seen this kind of like the thing, this kind of like the parameters in the car. Once you're just going to add like the oil to the car, depending on if you are like the living like the cold region or like the warm area, you need to just choose either 10 or 30. So depending on the like the weather, that you need to just use the thick or thin oil. Okay, so I mean, this is for the 20 degrees. Imagine we're just going to use like the for 100 degrees, the dynamic viscosity, this kind of like coefficient, dynamic viscosity mu of the water falls from this figure, okay, to 0.284 times 10 to the minus 3. This is a 10 to the minus 3 kilogram per meter second. Just bear in mind the units of the dynamic viscosity, kilogram per meter second at the bottom of the ratio. Okay, so you can see here it just falls to this figure, and in other words, we can call this kind of like the water as 100 degree. We can say the water is thinner, okay, but this one is thicker at 20 degrees. But because like the thinner, and the density also dropped to 958.4 kilograms per cubic meter, compared to like the something that it was very close to like the 1,000, and showing that the water is getting lighter, because like the density is lower. So with the like the high temperature, it becomes like the thinner and lighter. So that's the fact. So that's the reason we're just going to use like the two different types of the oil for the car. So please just work on that and see if you have like a car, if you are in like the cold area, for example, you are in like in some countries like the Norway, for example, Finland, or like the Sweden, what sort of like the oil you need to use compared to like the ones you are just living in like the south of like the Europe. So thin or thick, and why. We'll discuss about that later in the class. And The other things that you need to just bear in mind is like the concept of the viscosity, where it has come from. The Newton investigated this viscosity term by running or investigating and conducting a very simple test. Newton just used two large horizontal plates like this one. The lower one was fixed and the top one was mobile or movable. And by standardizing a liquid between these two horizontal plane, he just used this kind of like the test. And that's kind of like the area. This is like the plate. The plate has got the total area of A. Okay, so this one, and is free to move in response to a force. So we apply a force, for example, by pushing, for example, your hand or his hand, for example. We try to just push this one and apply the force horizontally to just push this one forward. And this kind of like the space between these two layers are filled with the liquid. Imagine this liquid could be oil or could be water. And he wanted to investigate and analyze what is the key factors on like the force. And we know that shear stress tau is calculated by the divisions like the F, or the force divided by the area of the plate. So here we just have this one in this kind of like a relationship. Tau is like the F over A. So Newton concluded, or within his experiment, he just get to this point, and that the velocity, once you just apply the force, the velocity of the upper plate and the distance between the plate has got some relationship with the force, and the F is directly proportional to A and V. Okay, so meaning that if the area increased, so the area of the lighter plate increased, he needs to apply more force. And also he get to this point, if he wants to just have the higher velocity, he needs to apply more force. So there is like a direct relationship. This is like a proportional, direct proportional to the A and V. And interestingly, he just get to this point that the force has got the inverse proportional to D, the distance between the two plates. So for example, for a smaller D, he has to apply more forces. And for larger distance between the two like the plates, he needs to just apply less force. So indirect proportional. So this is like a proportional. So the three parameters, A, V, and D, and on the left-hand side is F. So in order to just make it as equal, so we need to just use like the parameter. In this case, we call it like the mu, or is it exactly the term that we use in the table? This is like the coefficient of dynamic viscosity or absolute viscosity. So that is denoted by mu, and the unit is kilogram per meter second. So because this one, remember we said that F over A is called, you learn this from a structural analysis and design, a structural analysis and structural mechanics, that this division F divided by the area is called shear stress. Okay, tau can be easily used by that kind of like the term substitute. F, if you rearrange A to the left hand side, so F over A is the shear stress. Okay, so we can just replace with the shear stress tau in here on the left hand side, and the right hand side is like the absolute or dynamic viscosity times velocity divided by d. So this is the formula that we have, and we use it for some sort of like the findings and calculations here. Or tau can be written here as in different levels, can be written as like the mu du over dy. So the du here is like, in some references you can see here, du is like the difference of the velocity. The difference of the velocity for any 2 points here, you can just write here. So based on that definition, we can just carry on. And we just learned that a dynamic or absolute viscosity mu but we can just write find another relationship between this parameter and the coefficient of the kinematic viscosity, which is denoted by nu. Okay, nu is like a Greek letter. Nu is like this one. You can write it here. Sometimes you can see in some other references. So kinematic viscosity, or nu, the relationship of with the dynamic viscosity, you need to just divide that one. You need to divide the dynamic viscosity by rho, or the density. You can get the kinematic viscosity. So just remember this formula. If you are told or if you are given the kinematic viscosity, but you need to have like the dynamic viscosity mu, you need to just use this relationship. So it's very simple. You only need one of them. So if you have any of them, you can easily calculate the other one. For example, nu for the water is like the mu over rho. So for example, if you have like a lookup table, you have like a mu, you can divide by 998.2 from the same table, for example, and you can easily calculate the nu, the kinematic viscosity, in this formula. 1.007 times 10 to the minus 6 meter squared over second. Just please pay attention to the unit. By using the dimensional analysis, you can easily see what is the unit of this. So meter squared over second. So at 20 degrees centigrade. And for the oil at the level of the SAE 30, you can easily use the same formula. If you have like a mu0 or dynamic viscosity divided by rho, or the density, you can easily calculate that one as well. So this is the viscosity.